All right, so in this video, we're going to take a look back at this polynomial that we built for this modeling quadratic for our e to the x function. And we saw that I had written down here that the formula to model the graph of e to the x should be 1 plus x squared over 2. Well, I guess we'll see if that works. Example 2. Find the local quadratic approximation of e to the x at x equals 0. Let's see if it actually comes out as this formula. I'm going to use the boxed formula up here to help me. All right, so let's see what we got. We see that I just need to find each of these coefficients. So I'm just going to start by computing what is f of 0? Well, that would be e to the 0, and that's 1. So apparently the thing that goes right at the start should be the number 1. I'll then also be able to say f prime of x. Well, that's pretty easy. That's just e to the x, right? And so from that, I can conclude that f prime of 0, which is what I'm supposed to put in front of x, well, that's just going to be e to the 0, and that's still 1. I can then also determine that f double prime of x, well, that's still e to the x. So f double prime of 0 is still e to the 0, which is still 1. And that should apparently be over 1, or over the value of 2, and that will make the coefficient of x squared. So if p of x is supposed to be equal to f0 plus f prime of 0x plus f double prime of 0 over 2 times x squared, then p of x should be equal to, and I'll just start filling in the pieces. F of 0 is 1, f prime of 0 is 1x, or 1, but then times x. F double prime of 0 is 1. That's got to be put over 2, and I got to have an x squared. So my polynomial is 1 plus x plus a half x squared. Is that the same polynomial that I had up here? Yes, it is. That's exactly the same. So that's where that polynomial comes from. And remember, the goal here is that we're trying to model this function. So I should be able to say then, if I plug in numbers for x into e to the x, and they're complicated, maybe like e to the 0.5 that we looked at in the last couple videos, then we should be able to say that this will only make the approximation better. So let's see. I'm going to go back to my calculator here really quickly and highlight the following. We saw up here that when we did e to the 0.5, let me just recrunch it out here. We did e to the 0.5, we got this value. And I think when we looked at the linear approximation that you should have back on the first page, we estimated this value at about 1.5. But let's see what would happen if instead of using the line to estimate this value, we used this quadratic. So notice I would have to plug in the value of 0.5 in for x, and I want to see if this gets me any closer. Oh, it does. That gets a lot closer. So I can now have the first decimal place even locked in at this point. The quadratic approximation is doing better, and that's a really, really valuable thing. So we can see how we can start to use this sort of a formula to build quadratics that model functions. And we can model any function as long as we can find its first derivative and its second derivative and evaluate them at 0, and of course evaluate the original function at 0. If we know how to find all the numbers that go in front of the x's, we can build the quadratic. Okay, in the next video, we're going to try to take a look to see how can we maybe plan to extend this technique even further.